All right, this is Electrical 2, Module 9, Grounding and Bonding, Module number 26209-20. This is the 10th edition book. I'll be going quickly through this, just as I think grounding and bonding is very, very important as far as safety. It's just not the most exciting thing in the world. So let me pull up my slides. We'll get going. So, again, this is grounding and bonding, electrical 2. This is module 9. Trade terms, first page. Those are important trade terms that you should have heard most of them before. Bonding is just connected to establish electrical continuity and connectivity. Talk about that a bunch, but different components of grounding systems like ground rods or grounding conductors. Grounded conductor. I will push this till I'm blue in the face. The grounded conductor is not the grounding conductor. So make sure there's a lot of different terms that sound the same. Grounded conductor, grounding connections, grounding electrode conductor, neutral conductor. Again, all these sound the same, but are different things. So make sure you look through those trade terms. No highlights. I don't have any highlights at all on page 1. Flipping over to page 2. Page 1 is talking about this, but it's the picture that's up on the board. Zoom in here, and I've got this picture, a good picture of a panel up here. We've got a couple things to highlight. The ungrounded conductors. Those are your service conductors at the top. You want to highlight this up here. Your ungrounded service, 120, 240 volt hot wires. So coming into your main panel, those are the two wires coming into your main. The other thing to highlight is the neutral conductor. So you have your two ungrounded conductor, also known as your phase conductors. Then over here you have your neutral or your grounded conductor. Your neutral is your grounded conductor, not your grounding conductor, your grounded conductor. Over here, ungrounded conductor, live wires, phase wires. Neutral conductor, it's going to be your white, sometimes maybe gray. Neutral, grounded conductor. The other thing to note, to highlight, other two highlights, is the grounding electrode conductor right here. Grounding electrode conductor, so that's what's running out of your panel, usually to like a ground rod or something like that. Ground plate, water pipe, something like that. And then also your main bonding jumper right under it. So this is just the screw that connects this like terminal block to the panel. So it makes sure, and usually, not usually, I think it's required to have like a green finish on it. So you got your main bonding jumper that connects your terminal, your terminal strip kind of to the backboard of the panel. That's why you could tell just looking at this panel, I got all my neutrals or my grounded conductors and my grounds on the same, so I can tell that this is a main panel. When you get to a sub panel, that's whenever they have to be separated, and your neutrals won't actually be, there won't be a main bonding jumper on your sub panel because your neutrals will be insulated from that panel. Moving on from there into 110 grounding and bonding. Everybody can see what's wrong with this picture. Somebody's pulled the ground out of there. That ground is what puts current back to the panel in order to trip the breaker. If you don't have that ground, it's going to be harder for that breaker to pop for a short circuit. 110 over on page 3. Actually, it's in 111, short circuits. Top right of page 3, that whole paragraph is highlighted. A short circuit is a conducting connection, whether intentional or accidental, between any of the conductors of an electrical system, whether it's line to line or line to neutral. see figure 2. So figure 2 down there at the bottom, or on this up here at the board, your short would be between your ungrounded conductors, so that's your phase conductors, or between those and your grounded conductor. Remember, your grounded conductor connected to the ground. This is your neutral. Grounded conductor is your neutral. 1, 1, 2, ground fault, different thing. Ground fault, the highlight is the one sentence, the whole first sentence of 112, a ground fault as defined by in the NEC Article 100 as an unintentional electrically conducting connection between the ungrounded conductor, phase conductor of an electrical circuit, and the normally non-current carrying conductors, metal enclosures, metallic raceways, metallic equipment, or the earth. So you can see your ungrounded conductors where it's touching earth itself, not the grounded conductor, but the grounding conductor or ground. So you need to know the difference between a ground fault and a short. Two different things. 120, types of grounding systems. Third paragraph in 120, I've got the first sentence highlighted, the equipment grounding conductor. Equipment grounding conductors. This is the actual wire that grounds your system. Is the conductive path used to connect the non-current carrying metal parts of the equipment, raceways, and other enclosures to the system grounding conductor, the grounding electric conductor, or both. So like anything that's in these pipes, all these pipes should be grounded. This is equipment that should have a conductive path back to ground. So if we had a ground fault, if the wire touched the box, that it would go to ground and it would pop our breaker because we have a spike in current. 121, grounding single phase systems. So this would be like your house or like the low voltage type system. Third paragraph, I've got 3 questions coming out of the third paragraph, and I've got everything highlighted except for the last sentence. So a lot of highlights here. Referring again to the diagram in figure 5. So that is this one right here. Zoom in on that a little bit. So that's figure 5 up there on the board. Referring again to the diagram in figure 5, conductors A and B are ungrounded conductors. That's your phase conductors. While the neutral is the grounded conductor. That's what I keyed in on. Not going to say it again, at least right now. If only 240 volt loads were connected, the neutral or the grounded conductor would carry no current. So here in the United States, everybody else thinks we're pretty weird. I guess I don't know other countries that use. So we use a split phase system. Is technically what it's called. A lot of people think we have like leg A is phase 1 and leg B is phase 2. It's not phases. They're all one. This is why it's single phase. This is inside the transformer, like on the pole at your house. So they've got 7,200 volts coming in. We got less coils on the transformer on the secondary side. And then your 2 legs coming into your panel, leg A and leg B, are on the same coil. So if we connect something up to that, so 240 volt loads, so your air conditioning, maybe your water heater, stove, stuff like that, those have very minimal 120 volt loads. So especially like your water heater only has 120 volt loads for unless it's a super fancy water heater, or if it's a storage type water heater. So our current just goes in and comes out of both legs. But where I have 120 volt loads, I would might be connected to leg A for my ungrounded conductor, and then my grounded conductor or neutral would be connected to the other side, and that's where my current would return for a 120 volt load. Rest of that, however, since 120 volt loads are present, the neutral will carry the unbalanced load and become a current carrying conductor. For example, if leg A carries 60 amps and leg B carries 50 amps, the neutral conductor would only carry 10 amps. 60 minus 50 is 10. Easy enough. Last paragraph on the page is highlighted. The typical pole-mounted service entrance is normally routed by a grounded. The typical pole-mounted service entrance is normally routed by a grounded or neutral messenger cable from point on the pole to the point of the building being serviced. The terminating the service drop. Service entrance conductors are routed between the meter housing and the main service switch or panel board. This is the point where most systems are grounded. The neutral bus and the main panel board. So going on, they say figure 6. Let's see if I got that picture on the board. So yeah, you can see it's on your page 6, but you can see there your main service panel is where the circle at the top up there. You can see where your neutral conductors are grounded in that main panel. Flipping back to page 5, 122. 122. First sentence on page 5 is highlighted. Grounding is required in the following situations. First bullet point is highlighted. Where supplied by transformers, if supply voltage of the transformer exceeds 150 to ground. So, supply voltage to the transformer. So, just looking at that, looking back at our transformer, our supply voltage is 7,200 volts to ground. That's a lot. That's a lot more than 150. So, if you're at 150 or more, you got to be grounded. Flipping over to page 6 and 7, they go through the grounding systems, 50 volts to 1,000 volt systems. Nothing highlighted there, but probably worth reading through the bullet points. 124, grounding AC systems over 1,000 volts. I've got a sentence, second to last sentence on page 7 is highlighted. AC systems over 1,000 volts must be grounded if they supply a mobile or portable equipment as covered in NEC section 250-188. So mobile or portable equipment, if they're over 1,000 volts. That's all I got for section 1. I'm going to move right into section 2. Section 2, lots of highlights on page 1. First highlight is the second sentence. A grounded system must limit the voltage on the electrical system and protect it from, second bullet point, line surges higher than that for which the circuit is designed. So if I had my house was designed for 240 volts, if I had a surge way over 240 volts, that main should pop and the voltage should travel out of the panel through the grounding electrode conductor. Next paragraph, last sentence is highlighted. In general, all the following electrodes that are present must be bonded together to form the electrode system. And then the third bullet point in that section, the one right above the note, the top right of page 9, is highlighted. An electrode encased by at least 2 inches of concrete located within and near the bottom of the concrete foundation or footing that is in direct contact with the earth. So those are the different ways that you can make an actual ground. Second to last paragraph on the page, second sentence is highlighted. The building also has a metal underground gas piping system, but this may not be used as a grounding electrode. Please don't ground the gas pipes. Page 10. There's some highlights that you need to have from this picture up on the board. So this is figure 10 on page 10. This bottom right highlight right here, plate electrodes online test question. Plate electrodes must expose not less than 2 square feet of surface to exterior soil, must be bare or conductively coated iron or steel, and at least a 1/4 inch thick. You also need the ground ring highlighted. Ground ring made of at least 20 foot of number 2 or larger bare copper buried not less than 2.5 feet below grade. Got those 2 highlighted on that picture. And then I got one more highlight on page 10. Last paragraph on page 10, first couple sentences are an online test question. rod, pipe, and plate electrodes must have a resistance to ground of 25 ohms or less. It means that it's got to have a strong connection to ground. If not, they must be augmented by an additional electrode space not less than 6 feet away. So if they have more than 25 ohms, you got to put another. Usually they drive another rod in the ground, and you got 2 rods connected together. Over on page 11, I got some ways. I've got this picture over on page 7, so you can see at the bottom, don't ground to gas piping systems. But I do have a couple components highlighted. I got the grounding clamp highlighted right here, and then over here, the grounding clamp is highlighted. So the grounding clamp connection must be made within 5 feet from where the pipe enters the building. So highlight those 2 spots on that figure 12. Grounding clamp, and then the grounding clamp connection. You've got a picture on electrodes up here on the board or on page 12. A couple of different highlights from there. This one right here, the pipe or conduit outer surface must be galvanized or otherwise metal coated for corrosion protection. That is an online test question. Another thing to highlight, this ground rod on the side over here, 8 foot minimum. Highlight that. That ground rod's got to be at least 8 foot. Ground rod is shorter than you, it's not tall enough. That makes students that big. 211, sizing the grounding electrode conductor. Last sentence on page 12 is highlighted. Table 250.66 gives the proper sizes of grounding electrode conductors for various sizes of electrical services. Page 13, first sentence on page 13, I have 3 questions that come out of the one sentence. The size of the service entrance conductor is determined from the ampacity of that system. First 2 sentences, sorry. Table 310.16, most used table in your NEC book, should be marked in your book, is used to determine the size of the service conductor from its ampacity. More often than not, you're using, depending on if you're using aluminum or copper, or you're using 3/0 or 4/0 wire coming into the house. Often, not always, but often. Moving on from there, other electrodes on page 14, 220. Highlights are over on page 15, so specific requirements for other types of electrodes. That first bullet point on page 15, the last 3 sentences are highlighted. Rod and pipe electrodes must be driven vertically unless a rock obstruction is encountered. If an obstruction is encountered, the rod or pipe may be driven at not more than a 45-degree angle to clear the rock. The other possibility is that the rod is to be buried in a trench that's at least 30 inches deep. Don't have a lot of rock down here. Usually down here in southeast Louisiana, it's not too bad to get a rod in the ground, but say back where I'm from in Tennessee, like there's a lot of rock in central and east Tennessee. They hit a rock, they got to make different choices for either getting through the rock or going at a 45-degree angle or burying it 30 inches underground horizontally. Moving on to section 3. Section 3, equipment grounding. We talk the different, still more trade terms that talk about different components of the grounding system. My first highlight is in 312, sizing and equipment grounding conductor. So this is what the conductor is what connects your panel to the actual ground rod. Second sentence of that has 3 questions that come out of it. Second and third sentence from 312. The size of the equipment grounding conductor is determined from the size of the overcurrent device that is protecting the particular system. So you're looking at your main circuit breaker to size that grounding electrode conductor. Table 250-122 is used to determine the size of the grounding electrode conductor. The same thing, like that note there on 17, like that's what you want to get off of that page. Then you go into this picture that I've got up here on the board, and they show more different things you have to watch for grounding. So I've got this bottom left with going over the water meter is highlighted. The effective bonding jumper must be provided a round grounding electrodes, water pipe at any locations likely to be disconnected. So your water meter has joints on both sides that can be taken out. So you have to jump over that so that a plumber or your city service person doesn't have to do electrical work to pull that water meter out. So you gotta make sure you jump over that. If you're deciding to ground to the water pipe. 320, grounding and enclosure. Last sentence, first paragraph of 320 is highlighted. These items are bonded together to ensure operation of overcurrent devices in case of ground faults. So all that's saying is that if your stuff's not grounded, there's a chance that your overcurrent device isn't going to trip because that ground is not carrying that fault current back to the panel. 321, grounding outlet boxes and devices. Last paragraph on page 19, first sentence is highlighted. Figure 23 shows methods of providing grounding conductors to duplex receptacles using several wiring methods. Next sentence is also highlighted. For example, if non-metallic boxes are used with type NM cable, no connection to the box is required. If you're using a plastic box, you don't have to ground a plastic box. You flip over to page 21. So that's figure 23 that they were talking about. They got this picture. I'm pretty sure that's the right picture. Yeah, so they're showing like non-metallic boxes. So they got non-metallic box right here. You can see if you're in your book, you can see these are blue. Most of the time these are blue or gray, but you're just bringing your ground wire in and connecting there, or you're making a connection and continuing on. With your metal boxes, you can either connect, like you need to bring a screw or a clip or something to connect to the actual box itself. And that's just because, say I have a hot wire come off of this receptacle and touch this box. That box and conduit is going to be electrified. And if it's not grounded, it's not going to trip. If I have an ungrounded conductor or a phase conductor, hot, whatever you want to call it, come off of this outlet and touch this non-metallic box, it's not going to heat up. It's not going to conduct electricity. That's all for section 3. Moving on to section 4. First sentence on page 23 is highlighted. Electrical continuity is the key to successful clearing of ground faults. That just means a good connection. 410, main bonding jumper. Second paragraph, first sentence is my first highlight. Since the main bonding jumper must carry full ground fault current of the system back to the grounded service conductor, it must be sized. Its size must relate to the rating of the service conductor that supplies the service. Next sentence is a separate highlight. Table 250-102C1 is used to determine the size of the main bonding jumper. Make sure that screw holds is big enough to hold all that current. Flipping over to page 24, 420. Bonding multiple service disconnects. Second paragraph, first couple sentences are highlighted. Our first sentence. Because this bonding jumper is located on the supply side of the service disconnect, the basic rule for sizing the supply size bonding jumper for bonding its various configurations is found in NEC section 250-102C. Next little short paragraph, the one sentence paragraph is also highlighted in relation to your little table, which is up on the board. So table 1 shows various sizes of bonding jumpers based on the size of the service entrance conductor. You're going to have a couple questions come out of that table, so make sure you do a little highlight on table 1, but you're going to have a couple questions come out of that. Moving on. On to page 25, 433, installing equipment bonding jumper. The second sentence of 433 is highlighted. When the jumper is installed outside The length is limited to not more than 6 inches. So if it's installed outside, the length is limited to 6 inches. Page 26. A couple long highlights on page 26. 434, creating an effective grounding path. First paragraph, whole thing's highlighted. As previously stated, to have an effective grounding for both grounded and ungrounded in an ungrounded system, the grounding system shall have an effective ground path to provide a permanent and continuous path. Size to safely conduct any fault current that is likely to occur, and it shall have an impedance that is low enough to limit the voltage to ground and to facilitate the operation of the circuit protective devices in the circuit. All that to say, you have to have a path back to ground so that all your breakers or fuses or whatever's in your panel will operate. Next highlights right before those bullet points on page 26. The grounded conductor or neutral in a grounded system serves two main purposes. Not a bad idea to read the first bullet point. It's not highlighted, but it permits the utilization of power at line to neutral voltage. This will allow the current carrying conductor to carry any unbalanced current. I highlighted the second bullet point that's up there in the top right of page 26. It provides a low impedance return path with a flow of bulk current to the source to facilitate the operation of overcurrent devices in the circuit. We got section 4 review on page 27. I'm going to continue on to section 5. Separately derived systems. So these are not your house. These are separately derived systems. Page 28, 510, grounding separately derived systems. That sentence before the bullet point is highlighted. Examples of separately derived systems include, but are not limited to. I've got the second bullet point highlighted. Generator systems that supply power where the neutral is not connected to the utility system, such as for carnivals, rock crushers, or batch plants. I also have the next bullet point highlighted. Generator systems used for emergency, required standby or optional standby power that have all conductors, including a neutral, isolated from the neutral or grounded conductors of another system, usually via a transfer switch. Both those have to be grounded. Going on to page 29, that big paragraph on page 29, it's like the third to last sentence that I have highlighted. A supply size bonding jumper. So, supply side bonding jumper, just so you know what we're talking about, looking at the picture on your page 29, supply side bonding jumper. That's that green wire right there. I would highlight that. I've got it highlighted in my book. Supply side bonding jumper is routed with feeder conductors from the transformer to the equipment grounding bar in the panel when the bonding jumper is in the transformer. Flipping over to page 31. .520 grounding at more than one building. 520, page 31. My first highlight is the second paragraph, first sentence. The grounded circuit conductor and the equipment grounding conductor must both extend to the second building. So you have the grounded circuit conductor, that's your neutral, and the grounding conductor must both go to the next building. Same paragraph where you see the green highlighted NEC table 25066, that sentence is highlighted. The GEC, grounded electroconductor, and the second structure is sized using that NEC table 250.66 based on the size of the feeder conductors. Up at the top of table 2, it's going to say that is a table for the number of conductors between structures. So that's what you have to have, how many conductors you have to have for different voltage systems. So you will have a quiz question come out of this table 2. I've got the 120 volt system. You have to have one ungrounded conductor. So that's only if you're bringing 120 volts somewhere. So if you're going to a garage and you don't need a 220 plug or anything like that, you have to have one phase wire going to that. So usually you have one ungrounded, one grounded, and one equipment grounded. So that's what you have to have for a 120 volt system. So you got at least 3 conductors going to that separate building. That's all for section 5. Moving on to our last section, section 6. Testing for effective grounds. So this is something that I've never done, but there's equipment to make sure that your grounds are good for big systems and stuff like that. Going through the trade terms on here, you got different trade terms for the equipment that they're using for this. I do have the touch voltage highlighted on page 32 in the trade terms. Touch voltage is the potential difference of the voltage between a grounded metallic structure and the point on the Earth's surface equal to the normal maximum horizontal reach, approximately 3 feet. All right. The first paragraph on page 32 is highlighted. An earth ground resistance tester, figure 34, what's up there on the board, may be used to make a soil resistivity measurement or to measure the resistance of the installed grounding electrode system to the earth. So you can use that to measure, like where you have to have that 25 volt or ohms or less to earth, like that's what you would use. Nothing else highlighted on page 32 and 33. Flipping over to page 34, measuring earth resistance, 610. First paragraph, the little 1-sentence paragraph in 610 is highlighted. Several methods are used for measuring the resistance to earth of a grounding electrode. One of the most common is the fall of potential method, which is shown in figure 36. So that's what's up on the board. You can take your fall of potential, and you've got different distances that you have to space your probes out to do that. The sentence that splits the pages, starts on 34 and ends on 35, is highlighted. The voltage drop, or E, between the grounding electrode X and the auxiliary potential electrode 1 is indicated on the voltmeter. Resistance R can therefore be calculated as follows. R equals E divided by I, Ohm's law. You might have to do a little bit of math. That's all I've got for pages 34 and 35, flipping over to 36 and 37. Nothing highlighted in these, so I'm not going to go over this stuff, but you can read through it, but nothing highlighted in 36 and 37. Page 38, 3-point test 620. I highlighted the heading, 3-point test, along with the first sentence. 3-point test, to measure the resistance of a grounding electrode with most ground testers, an auxiliary current electrode and an auxiliary potential electrode are required. That's in figure 38 and 39. The rest of that paragraph is a separate highlight. The current electrode is placed at a suitable distance from the grounding electrode under test, and the potential electrode is then placed at 62% of the current electrode distance. So page 40 or figure 38 and 39 show that if you want to go through the math on how to figure out where to put your probes and stuff like that. You're going to have questions based on that. But yeah, that's about all I want to say. Page 41, that second paragraph on page 41, first sentence is highlighted. It is usually advisable to plot a complete curve for each season of the year. So you want to do these tests. And now to the side of that, I wrote for new ground. This is for new grounding systems. So for new grounding systems, it's usually advisable to plot a curve for each season of the year. And that's because your ground resistance changes mostly due to temperature, but also due to like moisture in the earth and different stuff like that. So that you want to do a full year of measurements. Skip a sentence.
And the next sentence is an online test question. Measurements at established intervals in the future need only be made at the 62% point and if desired, the 10 foot on each side, providing there is no erratic deviation from the original curve. So that's if you're doing these measurements year after year. If your grounding is super important. That is all the highlights that I have. So you've got your section reviews, your module review, your supplemental exercise, and your quiz is ready to go on Canvas.